let's say we want to create a network or some application which would be secure. So what does it mean? What does it mean, secure connection? Um, let's just take a look at what encryption is. So let's say we have two computers and we want to send information from one computer to another in a secure way so that somebody who is between cannot read the text. So we want to send the text. Before that, we encrypt it. Then encrypted text is sent and the other end receives the encrypted text. And let's look at our internet uh, connection and let's ask ourselves, at which place should we encrypt the message? So, should we encrypt the message in the data link layer? For example, your computer is connected to your Wi-Fi router, and that is a point-to-point connection between two direct devices. It's a data link layer. So your Wi-Fi router sends information through wireless waves. So actually, if somebody drives up to your house in a minivan with a long uh, antenna, they can hear all of the messages that your computer sends to your Wi-Fi router and your Wi-Fi router sends to your computer. So we would obviously think that we should encrypt the messages in the data link layer, right? But let's also talk about data link layer. Let's say you don't have Wi-Fi. You connect your computer with an internet cable directly to uh, to the cable that comes from the internet service provider. So you have a direct link from your computer through Ethernet cable, which is shielded, to internet service provider's server. You cannot even imagine how many cables are buried under the pavements and streets in modern cities, because from each house, uh, a cable goes to the internet service provider. Okay, maybe through some routers, but generally it's, the land is full of cables. But the problem is that somebody can still tamper into this cable. It's harder. Somebody would have to have access to your house, or maybe find a location where the cable goes from your house to the street. But generally, the cable network is considered to be more secure. But let's say we are in a school. In the school, there are many cables running from computer to computer, from computer classroom to school server. Somebody can just dress up as an electrician, find some day where there's a small amount of people in school, and they can just go climb up the ladder to the router, cut the cable, and put some spying equipment in between the cable, right? So it's theoretically possible. It's much harder to do, but it's possible. So we would also think that we want to encrypt the data that travels from router to router through cables also. But in reality, I think that this is not done in practicality, because chances of cutting the cable is very small. Next is network. So let's say that you want to connect to Facebook. Facebook is located in America. So when you send the messages, when you connect to Facebook, let's say you want to go into Facebook, your pictures page, but you don't want other people to see those pictures. So you know that when you connect to Facebook, your message first goes, your message goes to Facebook, and Facebook now sends you your pictures so that they can be displayed on your web browser. Your picture files first go from Facebook to United States data center, so that data center can see all of the data that you're sending. and they can copy it, they can store it, and so on. Then this information is sent through submarine underwater cables from America to Europe and received, for example, at, I don't know, Germany, for example, maybe has the data center. So German data center sees all of your pictures also. They can see the data stream, it goes through their servers. Then from Germany, it goes to, for example, Latvia. So Latvian central data center also sees all bits that you are sending because you're using their cables. And then only then it goes to your internet service provider, which also sees the data. And only then it reaches your computer and the pictures are displayed on your screen. Okay. So we would think that we also need to encrypt data when we're sending it over network. So my computer should encrypt all data that is going out of its network card so that other computers cannot, other servers or routers that are on the path between my computer and Facebook do not see the contents. The contents are encrypted, so they cannot read them. They can copy and store, but they cannot read what's inside. Next question is about operating system. So transport layer is usually implemented in operating system, for example, in Windows. Okay, so Windows creates these sockets. So if I have browser, the browser does not connect directly to the network card. It asks the operating system to create a socket and to do the connection, because between this browser and my network card is the operating system. Only operating system controls the network card, whether it's Wi-Fi or wired. And this is how the viruses work. They are implanted inside the operating system. So when you connect to Facebook, even if you have encryption between your network card and Facebook's network card, the problem is Windows. Because if Windows has some virus, which, for example, forwards all of the data that you are sending from your web browser to the network card to, I don't know, for example, Facebook, maybe there's a virus which copies everything and sends it also to some hackers servers. So hacker can also see your pictures and your passwords and everything. So you would also want to encrypt data that goes to your operating system, because you don't know, maybe the operating system has a virus. So also the session is, session is more about communication sessions. I don't think you can encrypt anything. So generally, you would think that you need encryption in every layer between two nodes, between computers in the network, so that routers cannot see the contents inside, transport layer between operating systems so that operating system doesn't see the data that you are using, and so on. So all layers should have encryption, okay? However, if every layer does encryption, you understand that the encryption process would be really slow. You need to do 5 different encryptions before you send the message out. And encryptions between each router and encryptions between computers. That's a lot of encryption, and encryption, of course, takes time. The stronger the encryption algorithm, the longer time it takes to encrypt. For example, on embedded system, this RSA algorithm can take something like 10 seconds to encrypt, a long time. So we don't really want to encrypt everywhere. And now I will ask you the opposite question. Let's say we only encrypted data in the top layer, in application layer. If we only encrypt data inside the browser, and encrypted data is only then forwarded to operating system, the operating system doesn't really know what's inside the data because application already encrypted it. So operating system has no idea what is inside these ones and zeros. If operating system forwards the message to network, since the uh, information was encrypted in application, the network also doesn't really see what information is inside. So, and even if the network layer sends the message, the routers that forward the message, they don't know what's inside the message because it was encrypted by application. As a result, in reality, you only need to encrypt the information in the highest level. And this is why these 7, 6, and 5 are united like in the same subgroup, because application is presenting the data and also encrypting it in this presentation part of the browser. So this is why Google has enforced that all uh, servers need to do application level encryption, so that even somebody has a virus in your Windows computer, even somebody has tampered your network connection, even there is a router in the path between your computer and the web server, since all data is encrypted in the highest level, you don't care if somebody can read something, uh, your data is secure. So when you log into your Artus, for example, it happens in the browser. The browser encrypts the data so that even if you are connected to a Wi-Fi router that doesn't have password, or even if you're connected to a Wi-Fi router that also a hacker has guessed the password and can read all the stream, since you only send encrypted data through Wi-Fi, encrypted inside the application, and the Wi-Fi router already receives encrypted data, you don't really care. And actually, the Wi-Fi passwords that we have today, actually their purpose is not to make our data secure. Actually, it was a fix because in olden days, servers did not encrypt their data in application level. Many times, actually, there was this program which was called Wireshark or something like that, where basically you open the program and you can see what your sister is browsing on her computer, for example. I have a sister, I could see what she was browsing on her computer because this Wireshark application worked in data link, and it saw all of the traffic that went through our Wi-Fi router. Today, it's not possible anymore because if she wants to connect to the server, then all the data that is sent forward and back is already encrypted inside the browser, and I cannot see what she's doing. The only thing that I can see is the website name to which a person is connecting, because network layer needs to know what server you want to talk to. If you give all the data encrypted, then the router doesn't know where to send your message. So basically, it would look like this. The beginning is, for example, to facebook.com, user ID so that Facebook knows which connection it is. And then the payload, all of the data would be encrypted. And Facebook receives the data. It sees who connected. It knows your password, so it decrypts the information with your password. And then it sends you back your photos or your messages or whatever. So application layer is the one where the encryption happens. And it should happen only in this layer. And if it happens in application layer, you don't have to make encryption algorithms in any lower level. It's just not necessary. Okay, so now we need to, I think we will spend the next 4 weeks talking about encryption, because encryption is rather wide topic, and it there are just some basic things that you need to kind of understand. You don't have to be encryption masters, you just have to understand some principles. So the first principle is encryption should happen on the highest level possible, because you have to assume that any other lower level is compromised, is hacked. So if you encrypt in browser, you don't care that network is, for example, corrupt. All the message has been already encrypted, so nobody on the network can read the message. You know your password, Facebook knows your password, and Facebook at its top level server side only decrypts the message uh, and sends back encrypted data. So now we need to talk about encryption. And to talk about encryption, we will first look at the history, at the beginning of encryption. And one of the oldest documented encryption algorithms is called Caesar's code, or Caesar Cipher. Let's see. Okay, a lot of advertisements. Okay, maybe this will be better. So the idea is the following. It's sometimes called ROT 13. Yeah, let's look first at ROT 13. ROT 13 is a code where you exchange each letter with the letter that is 13 letters ahead of your letter. And since Latin alphabet has 26 letters, ROT 13 lets you do it bidirectionally, like in this table. So you write a text, a simple text, and this was done 2000 years ago, and this was considered like really strong encryption, the encryption standard. Nobody knew how to decrypt it. So here you have it. Instead, let's say you write text hello, and then you just move each of the letters to the letter that is 13 letters ahead. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So you replace H with U, you replace E with R, you replace L with Y, the second L also with Y, and you replace O with B. So the encrypted message looks like URYYB. So if you send this message over the network, the router sees URYYB. It has no idea what you are sending here. Even if the hacker reads this message, he has no idea what you meant. Okay, because he doesn't know that you used ROT 13 encryption. And instead of 13, you can shift all letters by 1, by 2, by 3 positions, by 26 positions, 25 positions. So it doesn't matter. But ROT 13 just lets you replace them directly. ROT 13 is used in online forums as a means of hiding spoilers, punchlines, and so on. Also, it is used, for example, in geocaching. You hide this geocache box somewhere and you put its location on the internet. And for example, you encrypt its location by ROT 13. So, it's a simple algorithm. People can just guess that it's the algorithm that's used, so they can find it, but it's not overly simple, not overly complicated. And decryption happens, backwards. So if we're using ROT 13, I receive the letter U, I go 13 letters back, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So instead of U, I decrypt to H, from R, I decrypt to E, from Y to L, from Y to L, and from B to O, and I can read the message HELLO, hello. So the receiver just decrypts it backwards. So this is a very simple encryption algorithm. Now, please write in the chat box, do you think it's a secure method of encryption? In the chat box, you can try to, for example, write, do you think it's a secure method, or is it not secure? Is it easy to guess? Okay. So somebody says easy to guess. Okay. By the way, here's a beautiful picture. So this is also called a rot, from rotation, because for encryption and decryption, you can just make these two disks, each of them having the Latin alphabet, A, B, C, D, E, F, G, H, and then you just rotate the center part by, for example, 13 or by 5 forward, and you can quickly just do the encryption. So this disk has been rotated by 13 locations forward, so I can see that A translates to N, and Y translates to P, and so on. So M to B, L to C, and so on. And decryption would happen in the opposite way. You see N, you know that it's A, you see V, you know it's S, and so on. So with this disk, you can encrypt and decrypt. And you know, people in the olden days, in Caesar's times, most people didn't even know how to read or write. So this cipher was like really secure for them. Most people would see this object, they wouldn't even know what the hell it is. So, you know, it was an okay encryption. But here's the problem with the Caesar cipher. In something like 17th century, it maybe wasn't really that much of a problem. And also here's an example of input code. And then here is all letters shifted by 13 bits forward. And here's some pseudocode how to do it. And here's decrypted. So here's the problem with this algorithm. When people invented computers, it became really simple. The problem is that some letters in alphabet are more common and some others are not that common. For example, letter E is the most common letter in the English alphabet. So if you take a long text and you encrypt it, then the letter that you exchanged for E, that letter will be very frequent, appearing very often in your text. Let's check out, for example, let's use this rot 13. So in normal text, letter E would show up 12.5% of the time. Actually, something like close to 13% of the time. If you take the text and replace all E's with R's, now letter R will appear just as many times as letter E was in the original text, right? So having even one paragraph of text will show that there's this letter R, which is suspiciously frequent, and it will be approximately 13% of the letters will now become letter R. So the hacker just takes your encrypted text, finds that letter R is the most common, and it will just replace it with E. And since the hacker knows that you are using ROT 13, he actually knows that he has to shift any letter by 13, and he will get the original plaintext and your code will be cracked. Even if you shifted letters only, let's say, by 2 positions, instead of ROT 13, you use ROT 2. So E becomes 1, 2, it becomes G. Well, then the letter G will be extremely common in your text. Letter G will be appearing 13% of the time. The hacker says, okay, letter G is really common, so the uh, programmer must have exchanged E for G. G is 2 places ahead of E, so if we're assuming that he was using ROT13 algorithm, well, then we just shift all bits 2 positions back, all letters 2 positions back, and we immediately crack the code and get the original message. And I think that there's even this letter frequency counter online. So here we don't know, let's say we get this, let's say we get this text, okay? So I'll just copy it. This is encrypted text. Here's the original text, but let's say some hacker interferes and the hacker sees this text. So, oops. I paste this text here. It's encrypted. Oh, it's encrypted code. What, I wonder what's written there. Now, if I click this, I don't know, it's like record input or something. So what I see is letter G is 75 times, letter R is 88 times, letter V is 52 times. I see that there are some letters that don't appear at all, but some letters appear more frequently than others. So for example, the most popular letter in this, oh, and I also can use this, draw a bar chart. So I see that letter R is the most common letter. So most probably the hacker replaced letter E with letter R. And because as you can see in this graph, letter E is the most common one. So if we are using this ROT13 algorithm, I have already cracked it because I know that I have to shift all letters by the amount which differs from R to E. For example, E is not very popular. So letter R is the most popular. That must be E. I check out the second most popular letter is letter T, which is something like 9% of the time. So letter T is not very popular, but letter G is. Let's see. I go here. I check out that letter G is replaced is replacement for letter T, and I check it out here and it matches. R is the most popular one, G is the second most popular one, which is also a letter T in this. So I already know that this text has been encrypted using ROT13 algorithm, and I can just move all the letters 13 positions back and decrypt all the message. So ROT13 is very easy to crack on modern computers. It basically takes, I don't know, 10 seconds maybe to decrypt it. So that is the first algorithm. Now let's see, and actually the first, analysis of this algorithm only appeared in something like 17th century. You had books, for example, and people wanted to encrypt the messages, and people could just count the letters and decipher it. But the problem is that without computer, it takes a lot of time. It takes a lot of time to count the number of each letter and then realize which letter is which. So If it is a war effort, let's say that you are spying on the neighboring tribe on when they want to attack you, well, of course, you would dedicate some resources. Several people would sit down and spend their days decrypting the messages, counting the numbers, replacing them with the most popular letters. But, it wouldn't really be something widespread. Introduction of computers helped a lot. So what a naive person would think about is, well, okay, so moving all letters by the same number of positions would be stupid. But how about if I do it differently? Let's say I don't move all the letters by the same amount. Let's say that I just replace A with N, but B, for example, with D, and C with J, and E with V, for example. Let's say I don't move all of the letters by the same, by a fixed position, but each letter is moved forward by a different position. There's a method to hack that as well, and it's the following. It doesn't matter by how many positions you move letter E, the new letter will still be very popular, more popular than other letters. It will be 13% of the time. So if I replace E with M, the M suddenly becomes 13% popular, and so on. If I replace T with some other letter, which is not exactly the same amount of letters ahead, but for example, with Q, with some randomly chosen letter, then Q will become the second most popular letter. And the hacker, yes, it will take a little bit more time to decode the message, but the hacker will just see which is the most popular letter and just replace it with E, the second most popular letter replaced with T, the third most popular he will replace with A, and then the hacker starts to stumble because some letters, the probability, the amount of the letters in the text is very similar. But what the hackers do is they start to look at letter pairs. So here's letter frequency in, for example, English alphabet. Okay, this helps us find E, A, and T. But there's a second thing, which is letter pair frequency. Oh, look at this. There's even an extended table. Relative frequencies of the first letters of a word in English language. So let's say you don't really know, for example, you have found E and T, and then you check out this table and you see that, for example, letter I is extremely popular in the beginning of the word. So if you see one letter being very often in the beginning of the word, that must be either letter I or letter O. And the final thing is, let's see, 1 second, is it here? The hacker also looks at pairs of letters. So even if we know, okay, letter E is R and T is G, there's also something called letter pair frequency, and letter pair TH is extremely popular in English language. So you are starting to look at pairs of letters. TH is a very popular, very common pair of letters, So if you see letter T and then the same symbol next to it, you know that that symbol must be actually encrypted symbol H. So you have found letter H also in the text. Then very popular is three-letter word the. So you can find that also. Then, and there are other pairs of letters that are popular as well. And so hackers can just run through some algorithms which they can write in the C programming language, and they can decipher the text and just, until they decode all of the words. And yes, of course, there are some letters that are very unpopular, for example, J and X, but usually the algorithms can decrypt the text to something like 99%, and the final 1%, for example, a human can read through the text, and the human will see, oh, there's a typo, so that other letter must be something else. So this method is broken by letter frequency. And however, 17th century scientists spent something like an entire century improving this algorithm yet more. Uh, let's see. I think they were called Wagner's codes. Enigma Machine. Mm-hmm. So I would need to find one second. I misspelled the name of the scientist. So in oh yeah, so there's this a group of ciphers which are called Wagner Ciphers, and they work in the following way. So the idea here is that instead of encrypting, instead of shifting all letters by the same number of positions, we would shift each letter by a different amount, and this different amount descriptor would be called the password. So this is the first time we are using passwords, or it is better called a key. So the idea is, for example, this plain text. Crypto is short for cryptography. So ROT13 algorithm would just move each letter by some letters ahead. The Wigner Cipher idea is that you have a key, for example, ABCD, ABCD, ABCD. Basically, the key is ABCD, and you just copy the key multiple times, so many times as long as the plain text. And the key tells you for each letter by how many locations to forward it. So A means 0 locations, B means 1 location, C means 2 locations, D means 3 locations, and so on. Z would mean 25 locations ahead. So the first letter C is not changed. The letter B means that the plain text letter needs to be put 1 position ahead. So from from R to S. C means 3 locations ahead, so Y, Z, A, so it becomes A, and the letter P goes 4 locations ahead, so O, P, so P, Q, R, S, so P becomes S. And here we start over, so this letter is moved one position, 0 positions ahead, next 1 position, 2 positions, and 3 positions. So as a result, in ciphertext, it would be harder to decrypt because each letter is shifted by a different amount of positions ahead. So it's harder to run statistics on this ciphertext because in some locations letter E, which is most popular, would be replaced by letter C, and some locations it would be moved, it would be changed to letter L, for example, and so on. So the statistics would be harder to run, right? So this Wigner cipher would seem to be unbreakable, right? Because you cannot run statistics on ciphertext because in each location, the letter is shifted by a different amount. So, however, this algorithm can still be broken for the following reason. The algorithm is the idea is the following. You have a key, and the key is limited in length. And once you write the key, then you write the key again and again and again. And so if a hacker knows that, for example, the password is 4 letters long, then the hacker simply runs separate statistic on the first letters, on the first, fourth, eighth, 12th, 16th, and so on letter in the ciphertext. And in these positions, letter E is encrypted with the same letter because the password letter is the same. The shifter is the same. So in those locations, letter E would appear very frequently. And okay, letter E, there would be some letter that shows up 13% of the time, that is letter E. So you shift all of the letters in that location by the difference between E and that encrypted letter. Then you run the same statistics on the second letters, on third and on fourth. Basically, you do the same that you did on row 13. You just separate the locations by the password length. And you can shout in anger that it's impossible to know the length of the password. You have to know the length of the password so that you know when it starts to repeat and at what positions you should run the statistics. But hold your horses. Let's be realistic. How long can the password be in real life? 16 letters, maybe 20 letters. Well, you just have to write a program which runs the statistics, simply assuming, let's imagine that the password is 1 letter long. Let's assume that the password is 2 letters long, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on and so on. Assuming that there's, for example, the upper limit, that password could not possibly be longer than 30 letters, and you will just simply get 30 different texts, and either a machine or a human can look at these 30 texts, and human will immediately recognize which of the texts is the plain text, because assuming another length of the password would most probably give us some random letters. So this Vigenère cipher is actually easy to crack. You just separate it by the locations of the letters. Okay. So, of course, for 17th century, when actually, it was described even earlier, but generally, in the 17th, 18th, and 19th century, where there were no computers, where people would have to run statistics on each position by hand, of course, that would be really, really exhausting. you wouldn't really do it. But on modern computers, it can be done again in tens of seconds, in seconds maybe. Within a minute, you would get a result. Okay, so however, this algorithm actually shows us one thing, a concept which is called one-time pad. You see, if the key was the same length as plain text, you cannot run any statistics on it because each letter is pushed forward or back by a different number of positions which are not correlated between each other, which does not repeat. So if the password was the same length as the plain text, if the key was the same length as plain text, each letter would be shifted by different location, and you could not run statistics, and the ciphertext would be impossible to crack. So you need to remember this. It's called one-time pad. And if the plain text and the key are the same length, then it's impossible to decipher the ciphertext because you cannot run any statistics. And of course, one-time pads have their own problems. So let's say you come up with a really wrong password. Well, how are you going to send the password? If you send the password together with the plain text, well, then if somebody steals the message, they can see the key and the plain text, and they can just, read the key and read the read the ciphertext and basically get the plain text. So the way it's done for some top security information that needs to be encrypted, it is possible to arrange one-time pad transportation. For example, let's say you want the most secure possible communication link between, for example, White House and Pentagon. You want White House to send a message to Pentagon in such a way that it is impossible for anyone to interfere, read the message, and decrypt it. What would happen is, and it's been done, of course it's a big secret, so nobody can really describe how exactly, but the idea is that, for example, White House comes up with a very, very, very long key, for example, several megabytes long, and it prints it, for example, or copies it in a flash drive, and it holds one copy of key at its location, and it sends the second copy in a sealed envelope, in sealed locked box to Pentagon. And then using, for example, airplane and security and convoys, and they securely send the key to the receiver. And then after some time, when White House needs to send plain text to Pentagon, which is impossible to decipher, they can just use some parts of the key and encrypt the plain text and send the ciphertext, and they can send the ciphertext, as a writing on the wall where everybody can see it. Since nobody knows the key, the only two copies of the key are at the White House and Pentagon. Nobody can decipher this message, so it can also be sent over unsecured channel, and only the receiver, the White House, the Pentagon that has the original copy of the key, can decrypt. But as soon as they use some bits of the key, these bits must be immediately deleted and never used again. Because if they would use the key again, there would be statistic between two ciphertexts. These ciphertexts would be, as we say, correlated, and people could decipher either all message or maybe parts of the message. You know, in military messages, you don't want any part of the message to be deciphered. So one-time pad is the only absolutely strongest method of encryption. Everything else, unfortunately, has a possibility to be broken. For example, password can be guessed and so on. But a long one-time pad cannot be really cracked. Oh, it says it right here. In cryptography, the one-time pad is an encryption technique that cannot be cracked, but it requires the use of one-time pre-shared key. So the key is pre-shared through some secure channel, and the key is the same size or longer than the message being sent. Okay. And, you know, this is how British and American intelligence uh, spied on Russia, on Soviet Union, on USSR. Russians were lazy. Yeah, this is a funny story. So how Russians generated the password? They just took a coin, flipped it, and if it fell on heads, it would be 1, and if it would fall on tails, it would be 0. So using a coin toss, they would come up with an absolutely random, impossible to copy one-time pad. But the problem is, if you're tossing the coin, 8 coin tosses would only give you one byte of information. And if you want to send a movie that is 4 gigabytes, how many times do you need to toss the coin? So people got like really tired and lazy, and they decided, you know what? We're tired of tossing the coin. Let's just use this one-time pad another time. And unfortunately, they grew lazy and they started to use the same one-time pad several times. And, you know, the spies were not lazy. They checked out what if they used the one-time pad several times. They realized that yes, they were doing it, and they were able to decipher the messages. And you can actually read in this article. I think that mm, it's also written somewhere here. So people are lazy, they reuse one-time pads, and these one-time pads immediately lose their security. So that's about it. And the Vigenère cipher principle can actually be upgraded in such a way that it becomes rather secure. So in this case, we have password ABCD. It's 4 letters long, so it starts to repeat. And if we encrypt plain text with this repetitive key, then we start to see statistics for the letters which are in the positions of the length of the key. However, the peak of these Vigenère ciphers was during the World War II. So this method is possible to crack, but Germans during World War II developed this famous machine called Enigma Machine. It was based on ROT13 and Caesar Cipher and Vigenère encryption methods. However, they made it in such a way that it was basically almost impossible to crack it, and British actually spent several years and a lot of best mathematicians available in the world to crack the machine, and almost failed. And there was only a lucky um, occasion that they cracked the German Enigma machine and were able to read some messages that Germans sent to each other and win the World War II. But generally, they almost lost the war because this machine was really well built. So let's talk about Enigma Machine, which was, we would say, um, the last Wigner cipher type machine in the world, the best, and yet marks the end of the era. So the idea is the following. This machine has a keyboard, so you can type in the messages, and the messages are typed on the paper, you know, on a list of on a pad of paper, and these messages would be sent as rolls of paper. So if you want to send a message, you just type, for example, my name is Andres. I would type ANDRS, Andres. But this machine has 3 or 4 disks with which we set the initial offset of the machine. And each of these has 26 different positions. So starting from 1, 2, 3, 4, 5, and 26. So let's say I set first number to 25, the second I set to 2, and the third I set to 7, and this is the password. And if you look at all the possibilities, so I can choose the first number in 26 different positions times the second number is 26 different positions times 26 different positions for the third number. So if somebody wanted to decipher the message, they would have to guess 1 out of 17,000 different combinations. And remember, during World War II, there were not really modern computers. So for modern computer, running through 17,000 different combinations wouldn't be such a big deal, but at that time they didn't have computers, so they could not possibly try all 17,000 different combinations. So, and what happens is I set these initial positions and they tell the offset of each letter that I type. So I press A, instead of A, it shifts the letter by the number that is, for example, on the first knob. And as I type the letter, these disks rotate by some amount, so that when I type next letter, the offset is different. And as I press the next letter, the disks rotate by another amount, which is determined by the letter that I press. And the offset for the third letter will be again different. So as I type, the offset of each letter changes because these disks rotate. So there is no possible statistic that we can run on the ciphertext, because on each letter there's a new offset which we don't know. And if I write letter E 3 times, the first time that I press it, it was, for example, replaced by letter T. But since the disk rotated, next time I press letter E, it's going to be replaced by something else, for example, letter H. And I press E third time, the disk rotates again, and it will be replaced, for example, by letter M. So by using this method, if you don't know the initial position of the 3 disks, it is impossible to decipher. And as you can see, here is the second keyboard. It was used for decryption. As you press these buttons, the disks rotate in the opposite direction. So they're doing the decryption, okay? So you can encrypt or decrypt with this machine. And the idea is very good because you cannot run statistics. So generally, this machine is, we would say, for those times, very strong encryption, if not impossible to crack. So how it works? So 27. And in this page, it somewhere said by how many locations each disk would rotate on each button press. So these are the rotors. As you press them, they would move ahead. And another very important thing about Enigma Machine is the following. Oh yes, and by the way, initially Enigma Machine had 3 rotors, and then later they started to build in Enigma machines with 4 rotors. So instead of 17 different combinations, you multiply them by another 26. So you get 456,000 different combinations. Brute force cracking the Enigma machine in 1945, absolutely impossible. You cannot crack it in those times with brute force attacks. Nowadays, you can, you just turn on computer, wait for something like 15 minutes, it runs through all of the combinations, and some Google machine learning algorithm can detect a readable text, you know. If you put a wrong combination, it's not that the machine would explode or you wouldn't get an output. If you put a wrong combination, you get output, but the text will be random letters that don't mean anything. Um, and you know, you can't read it, it's the wrong text. So these machines encrypt and decrypt, but if you put wrong password, the decrypted text is wrongly decrypted and doesn't mean anything, cannot be interpreted properly. And another thing that you have to know about Enigma machine is it was mechanical machine. So it had a lot of very small parts. And this made cracking Enigma machine even harder because during war, even if British attacked German um, German positions where there was an Enigma machine, well, Germans would just take this machine, throw it on the ground, it would all break and shatter because it's full of small details. And even if British would get this machine, it would be broken and they couldn't even put it together properly. They didn't know how to put the machine together back. So it was very hard for British and American and French armies to even get a working Enigma machine in their possession because Germans would just throw it on the ground, shoot a couple of bullets through them, and that's it. British couldn't even get the machine. And even when they got a couple, something like 2 or 3 of these machines, it was very hard to decipher or encipher anything. So now let's see if there is, yeah, only a handful of machines. So generally the algorithm is clear. Now the question is, can you come up with an algorithm that would help you find the key faster? So let's see. The way that so there's this breaking Enigma machine. Um, I think that the main problem with Enigma machine was that Germans used the same beginning of all of their messages that they sent. In the beginning of the message, they always wrote the weather forecast. And, you know, if you're fighting a war in winter, well, how many different temperatures do you have? You have temperatures between, let's say, -15 and -5. So, you know, you only have 10 different temperatures. So if you could kind of guess the temperature, I think that was one of the helping points. You could faster verify if you have correct password or wrong password, right? And to crack the Enigma machine, they actually had to build a machine that tries to decrypt the messages. Pause, exploit quirks of the routers, compiled catalogs, build a cyclometer to help make a catalog with 100,000 entries to try to kind of find the result faster. So you can read more about this Enigma machine, but this part kind of conceals the ROT13 Caesar Cipher era. So if you have some questions, you can write them in the chat box and I will answer them.